Okay, this lesson is on normal distribution. We're going to be able to identify what a normal distribution looks like, understand something called the 68, 95, 99.7 rule, and then use our calculators to find percentile ranks in a normal distribution. Okay, if you take a look at these two data sets, one from an apple orchard and the other from an orange grove, what do you notice? Well, you probably recognize pretty quickly that it's a fairly symmetrical shape. And then if we take a look down here at the mean is 1750, which I guess if we were going to draw this in here would be right around in here. You'll notice too that the standard deviation is 296, and the bins that we have down here are going by 300. So each of these is about one standard deviation away. So if we look over here at this one, the mean is 210, which would be about right here. Again, pretty much in the middle. And the standard deviation is 47, and again, the bins here are about the same. Okay. All right. So this is pretty typical of a normal distribution. A normal distribution is bell-shaped, similar to what we just saw on the previous slide. And it's symmetrical around the mean. You'll notice this is a new symbol for mean. We had been doing X bar. And then this is also right here used, this is mu. And it is just another version of mean that you'll see. And so one's population, one's sample. Anyways, the mean is right in the middle, okay? And then it's a bell-shaped and it's symmetrical around there. You can see this side and this side look the same. Okay, so that is called a normal distribution. Okay, what is true about this normal distribution is really something called the 68, 95, and 99.7 rule. And what that means is 68% of the data lies within one standard deviation. So I'm going to fill this out here a little bit. This is our mean. Okay. And then this will be plus 1. I'm going to do that for standard deviation, the sigma. And then this would be minus 1 standard deviation, right? This distance here is 1 standard deviation. This is 1 standard deviation. And so what it says here is that 68% of the data lies within 1 standard deviation. So that means from here to here is 68%. Okay, and then if that's true, then in here, 68% cut in half would be 34%. So this is then also 34%. Okay. All right, so then the next thing that it says is that 95% lie within 2 standard deviations. So 2 standard deviations is just 2 bins above and 2 bins below. So let's do, so this would be plus 2 standard deviations, and then this would be minus 2 standard deviations. Okay, so in this particular case, I think I'll maybe go with a different color here. From here to here, that distance right there is 95% of the data should be within 2 standard deviations. Okay, well, what does that mean? Well, if we go, right, if we have 68% within 1 standard deviation, okay, so if we say 95 is in 2 standard deviations, so if we go 95 minus 68, we get 27. So we have an additional 27% when we get to 2 standard deviations. So now if we cut that in half and say 27 divided by 2, we get 13.5. So that means here in this section is 13.5%, and this section here is 13.5%. Okay. So 95% lies within 2 standard deviations of the mean. All right, and then lastly, it says 99.7% lies within 3 standard deviations. So, okay, so this would be negative 3 standard deviations, and this would be positive. Okay. All right, so let's maybe do purple for this one. Okay, so from here to here, that distance right there should encapsulate 99.7% of the data within 3 standard deviations. Okay, so how much is this little section here and this little section? Well, let's do a little math. So if we say 99.7 minus 95, right, we would get, that's 4.7. Okay, 4.7. Now if we're going to cut that in half, that would give us 2.35. So each of those, this section right here is 2.35%. And this would be 2.35%. Okay. All right, so now what do we have left? If we have 99.7% within 3 standard deviations, then what do we have left at the very ends? Well, that would be 0.3%, right? So if I wanna, let's see, I'm gonna go right here in this section, then 0.3 divided by 2 would be 0.15, so this would be 0.15%, and this would be now we have that standard deviation section filled out. Some of these numbers, generally we say it's a 68, 95, 99.7 rule. I mean, technically it's 68.26. The 95 is 95.44, and the 99.7 is 99.72. But for our purposes, this is what we're going to use in this class. So hopefully that makes sense. This is the normal distribution rule that we will apply, and you'll see in lots of stats classes. Okay, so then how do we use this? If I said what percent of the data lies within the shaded region, right? In the very middle is the mean, and this is, you'll see everything shaded above that. So if the mean then is right in the middle, this would mean 50% has to be above that in a normal distribution. Now, if it's not a normal distribution, then the mean is not in the middle, right? Okay, and then this one has this bin here and this bin here shaded, but not this. So that's important to note. Okay, so this section is 13.5%, and this is 2.35 if we refer to our previous slide, right? Take a look. There we go. Yep, right here. Whoops. Right here. Okay, so, all right. So then we just need to add those two together. So if I add that together, I get 15.85. So that would be 15.85% of the data would be right there. Okay, so not too bad, right? All right, so then this one, again, I've got one standard deviation. We don't see the line there, but that would be one standard deviation here and then two. So this is the first two above. So we know that this is 34% and this is 13.5. So if I add that together, that just gives me 47.5%. Okay, so that's how you look at a graph to determine that, just kind of using that normal distribution as a guide. Okay. But, you know, it's not always quite that simple. So let's take a look at an example here. It says in 1817, a group of Scottish men had their chests measured. It was found that the chest circumference ranged from 33 to 48 inches, with a mean chest measurement of 40 inches and a standard deviation of 2 inches. You can see that this graph here has all that information. Okay. All right. What would you expect to be the smallest and largest chest measurements of the middle 95% of men? Okay, so now if you remember, middle 95% is 2 standard deviations away. So that's from here to here. So there's 1, 2. So that is 2 standard deviations away. So that would be plus and minus. So that's up to 44 and then down to 36. So what would be, you expect to be the smallest would be 36, and the largest would be to 44 inches. So that would be what we would expect. Okay. All right, well, the next question says, what would you expect to be the measurements of the 16% of the men with the largest chests in the population? Well, okay, there's the very middle. So we're talking about the largest would be this part right here. And we know that's 50% of the data. We also know that within 1 standard deviation is 34% right here, right? So if this is 50% and this is 34, from here on, all the way to the end is 16% of the data, right? So that would be the largest chests would be from 42 inches up. Or you could say greater than or equal to 42, which is probably a little bit more mathy, right? But either way, 42 inches and up. Okay, so that's just using that graph to help us figure that out and what we know about a normal distribution. Okay, so in this particular case, it's some information about recent SAT scores for college-bound seniors. They are normally distributed with a mean of 508. So I'm going to put that right here. This is 508. Okay, so that's right in the middle. Standard deviation of 121. Okay, so that means each section goes up by 121 or down by 121. So I'm going to fill this in. A 508 plus 121 would be 629. Okay. Let's make that a little bit smaller, and then add another 121, and that would be 750. And then again would be 871, right? Okay, now if we go the other way, 508 minus 121 would give me 387. Okay, do that again. This is a little bit easier. 266, and again 145. Okay, so I have that information. So now I want to see what they're asking for again. Okay. All right, between 387 and 629, now you'll notice, cool, that's this section here. We know that's within one standard deviation, so that's 68%. Okay. Greater than 387. Okay, so if we're looking at this one, that would be from here on. Now we know that this is 50%, right? 50% above. And then we know that this is also 34. So if I add those together, that would be 50 plus 34 would give me 84% of the data there. Okay, let's get rid of this so it's not confusing for our next part. Okay. All right. What percent is between 266 right here and 750? That looks like 2 standard deviations away, which we know is 95%. Okay. Between 266 and 629. Okay. So that's 34. This is 34. And this is 13.5. So that's 68 plus 13.5, which would give me, just adding those 3 numbers up, would give me 81.5%. Okay, that's how you can use a standard or a normal distribution chart to try to help you out and figure out where things are and what percent of the data lies within certain ranges. But as you can probably guess, not everything lies exactly within 1, 2, or 3 standard deviations from the mean. So what do we do in that case? Well, we can use our graphing calculators to help us in this situation. And we're going to try that out right now. So here's a question. It says, Ella and Alicia are comparing scores on their college entrance exams. Ella's SAT score was 1380. Alicia's ACT score was 32. The mean SAT score is 1,000 with a standard deviation of 200. The mean ACT score is 21 with a standard deviation of 5. Okay, who has the better score, right? We're comparing SAT and ACT. How do we do this? Well, we're going to use our graphing calculator, and it's a little tricky, but we can do it. So here we go. We're going to kind of focus on this part, and I'm going to show you some things to put in there. But we're going to enter in our calculator. So I'm going to pull up our calculator. I'll pull up the Let's just get rid of some of these. Okay. All right, so now you can do this on Desmos too, but we're going to use our just TI-84s to do this. So I'm going to press second and then the VARS one, and you get this screen here. We want the second one down that says normal CDF, okay? So this stands for cumulative distribution probability, and so that's the one we want to use. When we enter this, we want, if they don't give us a minimum value, in this case, they don't tell us what the minimum value, they just tell us that, like, let's start with Ella's example. She scored a 1380. That's her high score. The low score, you could guess, is 0, but we want to go all the way really down as far as we wanted to go. It's just a super duper small number. So you can see the calculator already has something in there. It's -1 EE99. So we're just going to leave that in there. It's a really small negative number. Okay. And then our upper one is going to be what they scored. Now, if they give you a minimum, so instead, let's say they said, what percent of people scored within 1100 to 1380, then I would put 1100 in the lower portion. But they don't do that here, so then we put a really small negative number. Okay. Then they do tell us the median of the SAT scores. The median of the SAT scores was 1,000, so we're going to put that in there. And then the standard deviation for the SAT was 200. Okay, and then we go over here and we hit paste. Okay, and then just enter. And you get this. You'll see it says 0.97128. So that means a little over 97% of the people, that's her percentage. She scored better than 97% of the people is Ella's score. Now we're going to do the other one. And if we go back to this, right? Okay, we go back to this. Alicia's score is 32. So again, we're going to do, we've handled 1380. We put in the mean and then the standard deviation. For Alicia, we're going to do a 32 as the upper bound, and then the mean and standard deviation. Again, they don't give us a range. If they do, you can do that as your min, or your lower is what they call it, and your upper. But we don't have that, so we're just going to go. Okay. All right, so I have this. Now we're going to do the same thing. Second VARS for distribution, and then we want the second one. Okay, so I'm going to leave the lower as that really small negative number, or really big negative number, however you want to think about that, I guess. And then our upper one here is whatever Alicia scored. In this case was a 32. Now, on the ACT, the mean is a 21, and the standard deviation 5 is what they tell us. We're going to do paste and then hit enter again. Okay, so now for Alicia, it says 90, or it's 0.98609. So that means she scored better than 98.6% of the population. So Alicia's score is better. Both scores are really, really good, but Alicia's is a touch better. Okay, so that's how we do this. Again, here's all of the information that we put in. Just to kind of remember, I have over here, this is the stuff that you just want to make sure is in your notes there. That's how we get in there. And then these other screens are just what they look like. You're going to get this, and we want the second one. Okay, and then what do we enter, right? This was the score, and we did not have a lower. Now, sometimes you will. And again, if they say, hey, from Alicia's, or let's just say people who score between a 28 and a 32, then like on this part, you would put 28 here as your lower and then 32. But they didn't do that, so we just keep it as a really small negative number there to make sure that we're good. Okay, so then our answer was, right, we got our two answers here, and this was Ella's score, 0.9712. And this was Alicia's. So whose was better? Well, Ella's score was better than 97.1% of the population, while Alicia's score was better than 98.6% of the population. So that means Alicia's score was slightly better. Sometimes when you do this, you might have to go out a few decimal places before you notice where the difference is. There might be really, really close. So if that's the case, go a little further out to make that determination. Okay. Hopefully that makes sense. That's really it for normal distribution. Go ahead and do the assignment. Hope it's easy. Good luck. See ya.